Again. Missing Alex. We are going to talk about the life and death now of stars. This is the life section of stars. We had the birth, last chapter. This is life, and then we'll have death next week. So I like this picture, so I wanted to ask you what's going on here. Because, I mean, it's cool, right? It's called the Ant Nebula. You see an ant, right? What in the world's going on?
Is that like a star forming in the middle? And like the jets of shooting out?
Okay. I'll want to suggest maybe that's a star forming in the middle with the jets of stuff shooting out. That seems reasonable, except for there's one thing that would say not as much. It should have at least, if it's just shooting out like this, if it's forming, it would have a lot of dust around it, so we'd still have the dust in the region that's not forming. So it's dying, right. So you have the exact right idea. It's just in the death stage, because when it starts with, everything's falling in, and then nuclear fusion starts. And when it dies, things fall in, and then you have a big explosion again. So this is the later phases of stellar evolution. The star is losing mass heavily. You can tell from the way that's distributed, and it's not spherically symmetric. There's something that made it so it's not spherically symmetric. Notice the false colors here. The colors are telling us sulfur is red, green is nitrogen, blue is hydrogen, and violet is oxygen. So this false color image is telling us what kinds of gases we have present there as well. So this is the kind of thing that happens when a star dies. Big, massive explosions. The last slide, should we get there, has like 4 pictures of stars exploding. So during the main sequence life, the main sequence is when hydrogen is being fused into helium in the core. So this picture on the left is showing the main sequence life. But as it burns the hydrogen, and when I say burn, what do I mean? Because it's not combustion. Combustion is the term that burning goes with.
But can you repeat that, please?
When I say burning, what do I really mean? It's not combustion. It's not true burning. Fusion, right. So when it's burning, fusing hydrogen, it's creating ash, helium. For every 4 hydrogen atoms that it fuses, it creates 1 helium. Now, the volume that the helium takes up is about the same as the volume the hydrogen takes up individually. So that means the volume taken up is shrinking by a factor of 4 for every fusion. And then you have that helium that just sits there. Is kind of like a lump, kind of like my Oakland Raiders are right now in football. Doesn't do anything, it doesn't help anything, and so it changes the balance of energy. Remember, we have the hydrostatic balance between the force of gravity pulling in and the force of fusion pushing out. And so as you get more helium buildup, you're going to have the thermostat slowly changing. And as it slowly changes, the star is going to get a little cooler and a little bigger. So what's that going to be doing on the HR diagram if it's getting a little cooler and a little bigger? What direction does it move if it's getting cooler?
To the right.
To the right. And what direction does it move if it's getting bigger? Up and to the right. So it's going somewhere in the up and to the right direction. It's getting more luminous in the process. Then we have something really interesting happening. Notice, this is still just burning of hydrogen. We haven't gotten to the end yet. But it's gonna start fusing helium in the end. It goes through some pretty interesting things. Stars grow in these death stages. As the star is running lower on hydrogen in the core, it actually grows larger. And so our sun is slowly growing larger, which shouldn't be too worrisome because it's slow. But if we were to stay on Earth for another 5 billion years, it would be very worrisome. This is showing just size comparisons for different stars so we get a feel for it. So the sun we think of as huge, and yet if you look at the Delta Booties, the sun is dwarfed by it. And Chi Cygni is just huge compared to the sun. And Chi Cygni is a small star compared to the largest stars. Chi Cygni is about 1/7 the size of VY Canis Majoris. Was it you that came up talking about the largest stars? No. Okay, yeah, that's right. Clayton was asking about the largest stars. We looked at Wikipedia, and Wikipedia, I'd say I think it's CY Canis Majoris. Well, I couldn't remember Canis Majoris. CY Canis something or other. See what I told Clayton? CY Canis Majoris is like number 7 on the Wikipedia list. But the thing is, all the ones above are very tenuously labeled for their size. So it's the largest one that scientists are really convinced it has that size. And it's about 7 times the size of that Chi Cygni. Huge. It's just a little bit smaller than the orbit of Saturn. The largest star, Jupiter, would be well inside it. Yeah, that's a huge star, right? How did they get so big? They're going through their death stages. And so as we go through the death stages, we'll see big stars occurring. Our sun will become big. When our sun is dying, the Earth will be inside the photosphere of the sun. Put another way, the Earth will be incinerated when the sun is dying. I had to say Beetlejuice 3 times. I can't say it out loud. How many people have seen the movie Beetlejuice? Probably none of you, right? You have.
Well, I've seen scenes of it.
Seen scenes from it. I've seen clips. Well, one of the jokes is if you say Beetlejuice 3 times, this God Beetlejuice comes and wreaks havoc on your life. Beetlejuice, this is the first image that was taken, I think it's of any star, does it say? The first direct image ever made of the surface of another star. That's pretty awesome. That is, instead of a point of light, you actually see that it has an area to it. So, Beetlejuice, you can see it's got a red color. It's a red giant. What does red tell you? Now, let's not say cold, but for stars, it's on the cool side, right? It's still hot. It would burn us. So Betelgeuse, a very bright star up there. That's yellow, you can tell. Yellow X will tell you which one is Betelgeuse. This one here is Rigel, which is the blue giant, about the same size. I think about the same luminosity as well. So, what's so special about Betelgeuse? Well, I have here a comparison of Betelgeuse and the sun. First thing you notice, Betelgeuse is 16 times more massive than the sun. It's not the same amount of material as the sun. So that is going to make a difference. The sun will never be this big because the sun doesn't have as much mass. The sun is actually going to die in a very different way than Betelgeuse will. The size, the sun's radius is 700,000 kilometers, where Betelgeuse 500 million kilometers. Between friends, we could say that's about 1,000 times bigger, right? It's obviously 7 times 1,000 would have been 700, but 700. But it's much, much bigger. If you wanted to be really accurate, you'd say 700 times the radius. Surface temperature, it's cooler. In fact, you have a problem with Betelgeuse, right? Except for it said the surface temperature, I think it was 3,400. This says 3,600. It's different. That's like 8% difference between those numbers. But Betelgeuse is definitely cooler than the sun. But its core temperature, the temperature in the core, 15 million, was that 160? Yeah, 160 million. Betelgeuse is really hot in the core. The reason it's so hot in the core is because it has so much mass and it's now fusing other elements. It's not fusing hydrogen anymore. That's run out. And so it's doing other things in the core, and it can't do that until it reaches very high temperatures. And so after it finished, when it was fusing hydrogen, now it still was hotter than 15 million during that stage, but it wasn't anywhere close to this. When it ran out of hydrogen, then things started collapsing, temperature and pressure goes up, started fusing helium, runs out helium, starts fusing higher things, and the pressure and temperature goes way higher as you start going to these heavier elements. Luminosity. It gives off 46,000 times the amount of energy per second that the sun does. Question?
So then you said that so it begins to get hotter as it's dying. Is that what you're saying?
The core,
Oh,
yes.
the core. Oh, okay.
And it's kind of funny as this occurs, you have more outward pressure, which makes it expand. But as it expands, as the three of you were discussing in class today, as the gas expands, the temperature drops. And so that's why it's cooler out there, because of the expansion.
But the core itself is hotter.
Yeah, the core itself is way hot.
Okay.
Now check this one out. The average density. 1.4, right about the same as Jupiter, right? 1.3 times 10 to the minus 7. 10 million times less dense.
Just from expanding so much.
That's right, just from expanding so much. And then the final number, how old is it? The sun is about 4.5 billion years. Betelgeuse is only about 10 million years old. We talked about this last class period. How can it be that Betelgeuse is so much younger and dying? Because it burns out faster. Now, I don't recall seeing in our textbook this calculation, but here is a good back-of-the-envelope way to calculate the lifetime of a star. You learned that the luminosity is proportional to the mass raised to the, I think our textbook said 3.9 power. And the amount of fuel is equal to the mass. And so you can take these and see that the rate at which it burns fuel is going to be proportional to the energy per second. Luminosity is the energy per time. The rate is proportional to luminosity. And so the lifetime should be equal to the fuel over the rate at which you burn it. Think about your car. You have, let's say, 15 gallons of fuel, and if you burn, let's say, 30 miles, or you go 30 miles per gallon, you can calculate how far you can travel by taking the amount of fuel you have divided by the rate at which you're burning it per mile. Same thing we're doing here, except we're doing the amount of fuel per time for our rate, and hence we're getting the time for the lifetime. And so if we put in those numbers, the fuel is proportional to mass, and the luminosity, the rate, proportional to mass is 3.9. Nice. And I should, well, that is equal, but I don't. So it's roughly, the lifetime is roughly proportional to 1 over mass cubed. So you take something like our sun, we use that generally as a reference, and we say another star's lifetime is going to be, so time for a star is equal to the lifetime of our sun divided by the mass of the star divided by the mass of our sun raised to the 2.9 power. Between you and me, us being friends and all, let's just say 2.9 is 3. So if we were to take the ratio of the masses here, the lifetime of the sun is 10 billion years, 10 to the 10th years. Divide that by 16 cubed. 16 cubed is 256 times 16. Here, I'm looking for my best calculator to do simple stuff. So we have 16 cubed. So it's going to be 10 billion years divided by roughly 4,000. And that gives us a proposed lifetime of about 2.5 million years is what I actually would get with this calculation. Or, yeah, 2.5 million with this calculation. Obviously, it's a little bit off, but you can see the lifetime should be much shorter for a more massive star. I'm wondering about that 3.9 number there, given that it's way off. 3.5, I think, is what I had from another source. Okay, here's a graph then showing stars going from when they first join the main sequence. So remember, we talked about before the birth line, and so I'll draw in the birth line. I'll erase it eventually, but I'll draw it in. So the birth line starts out here, comes up and comes down and goes, I don't remember the exact path, but something like that. And then it's going to burn across the main sequence. So the next step, main sequence, is it's going like this. Oh, come on, really? It's going like this across the main sequence, getting bigger in radius, cooler in temperature, higher in luminosity, and then it comes off the main sequence. So this is the birth here. The main sequence is going to be the band that's connecting these dots. So it burns across that main sequence. One of the reasons we believe the sun is halfway through its life is by looking at where it falls in that band of the main sequence. It's not at the bottom of it. It's midway through somewhere, and based on that position, scientists have determined it's about halfway through its life. But now we want to focus on the death part. So what happens at death? You see that there is a pretty distinct shift there when something bad happens. What happens? It runs low on hydrogen in the core. Runs low on hydrogen in the core, so what happens? The rate of fusion in the core drops. Rate of fusion in the core drops, things start collapsing in. Stars starts to get smaller. But then you have two things that can occur. First, you have, and it kind of depends on the size of the star exactly when things will occur, but you have a ring or a shell of hydrogen fusion that starts outside of the core. So the core has all of this helium in there, just this clump of helium. And then outside of that, you'll have a shell that's fusing hydrogen. And that shell then goes whoop, and quickly goes out through the star. Most of the mass of the star was in that core. And it quickly goes through, going outward. And as it's going outward, it's dumping more helium into the core. So the core gets more dense with helium, keeps getting compacted until the temperature in the core reaches a high enough temperature and pressure for helium fusion to occur. And when helium fusion occurs, well, then something special happens. Helium fusion will cause, depending on the star, either a big burst of energy called the helium flash, which I have on a picture coming up, or it could start slowly. The difference depends on quantum physics. Quantum physics says that you cannot have more than one identical particle in the same energy state. And in the nucleus, you have all of these helium atoms, and you have electrons. And those electrons are packed very, very tightly because of all the pressure. And the electrons get packed so tightly that you cannot compress them anymore. And so when that happens, we call it degeneracy. If you try to compress them anymore, you start to run into some quantum physics problems. And so then the temperature just goes up everywhere, and basically the entire core starts fusion at once. And so you have a huge eruption when fusion starts. That's the helium flash. If you have a star that is large enough, it actually won't do that. It will start fusing the helium before it reaches the electron degeneracy, and then it just starts at normal and you don't have the flash. After you have helium burning in the nucleus, well, it goes to the next slide. So this here is, you have the hydrogen shell burning out, and it stops when the helium fusion begins, I believe. Here's comparison for lifetimes of stars. I did the comparison, or I did the calculation for the, you know what? No, that was not right. Anyway, I did a calculation for Betelgeuse, and obviously I got a different number. It could be that I did the calculation wrong. It's not beyond the realm of possibility. But the lifetime for a very massive star like an O5 is just 1 million years. Where's the sun on this chart? Just below the 9 million, right? This is 1.1 solar masses, 6,050 G0. The sun is G2, 5,800, 1.0, and 10 billion. So the sun has a lifetime that's about 10 times longer than the lifetime of Betelgeuse. And I said 10. Did I say 10? I should have said 1,000. About 1,000 times longer than the lifetime of Betelgeuse, and 10,000 times longer than the lifetime of an O5 star. Bigger masses died much, much earlier. And these small masses, a K0, burns pretty hot, only 80% of the sun's mass not far away, 14 billion years. Why did they put that one on the chart? Because to the best of our understanding, the age of the universe is 13.8 billion years, which means no K0 or below star could have ever died, because the universe isn't old enough for them to have died. Yes, it's not. It's the next one has a link. I want to show you a video. There's some really cool videos. How many people have watched the videos from the textbook? There are links to NASA. They're not made by the textbook. No? There's another cool one about an HR diagram that I was going to show earlier and didn't get to. I'm going to show this one here. How do we know about these progressions? I just showed you what happens with a star dying. How do we know that? Hot tip, it happens way too slowly for us to have observed a star going through all those steps. So how can we know?
Just look at the same size of stars and what phases.
This man's a genius. It's exactly what we do. We look for stars of the same size at different ages. How do we do that? It starts with clusters. Clusters of stars. We talked about star formation. Star formation in a nutshell. You have a molecular cloud of gas. Shock wave comes through. The compression causes gravity to take over, forms a bunch of stars all at the same time. So you have clusters of stars that are all roughly the same age. Now notice it is roughly. They're not exactly the same age, so you're not going to see a perfect one-time snapshot. But if you look at the stars from a cluster, you're going to see stars of all different masses at the same age. And so you can say, okay, at this age, this is where stars of different masses lie in the HR diagram. So we're going to watch a video that shows how that works. There are two fundamental types of clusters. Globular clusters, which this is both globular clusters, it's the same thing, just different way of showing the data. But we have globular clusters and we have open clusters. Open clusters are smaller clusters with way fewer stars. Globular clusters, larger clusters with a lot more stars. There's also a thing called an association that's even less than an open cluster. So let's look at the comparisons here and then watch a video. So the comparison. So notice the different types of stars, globular clusters. Globular clusters are called globular cluster because you just see black on black is a perfect contrast situation. You see that these stars just get denser and denser as you get toward the center. Globular clusters are globed together with higher density at the center and less as you go away, very clearly globed together. Open clusters look like this. You don't have that packed together look. So globular clusters, how many are in our galaxy? Only about 150 that we know of. Globular clusters aren't that common. Although it turns out when you look at objects in the sky, you see a lot of globular clusters because, well, there's a lot of stars there, makes them put off more light, generally speaking. Open clusters, there's thousands of those. And then the associations, also thousands. So there are a lot more situations where there were smaller numbers of stars formed at once than situations where there are a lot of stars formed at once. Also, globular clusters can stick around for a very long time. They stick around for a very long time because they have so much gravity holding them together because there's so many stars. The open clusters and associations having less mass are more likely to stray apart. So we don't find old ones. You notice down the bottom, the typical ages, globular clusters billions of years, whereas open clusters a few 100 million years to, in some unusual cases, 1 billion years or so, and then associations up to 10 million years. Right? They dissipate. You might still have stars that were originally part of an open cluster or association, but you just don't know anymore. They look like they're isolated. Okay, going up to the top again, the location. We haven't talked about the Milky Way galaxy yet, but the Milky Way galaxy, think of it just like our solar system. Our solar system is in a disk, right? But we have like the Oort cloud that's a spherical shell around it. We have the same idea with our galaxy. We have the halo, which is that region above and below the disk that would be equivalent to the Oort cloud for the solar system. We have the disk, well, I don't think I need to go further there. That's where most of the stuff is. And then we have the central bulge, which is near the center of the galaxy. So you find globular clusters in the halo and central bulge. We've talked about where the center of the Milky Way galaxy is. I said it's important to me that you can point it out. Where is the center of the Milky Way galaxy now that we've established? It's important to me. Yeah, just out of the pouring thing from the teapot. Yes, the spout. Just out of the spout from the teapot of Sagittarius. So, how is it determined that that was the center of the Milky Way galaxy to begin with? Well, it goes back to Harlow Shapley. Harlow Shapley was studying globular clusters. And he saw there's a lot of globular clusters over there in the direction towards Sagittarius. And he theorized the only reason there should be a higher concentration in one area would be if that area was maybe the center of the galaxy. And so based on that, he determined that must be the center. He did some calculations of distance using variable stars. He got the wrong distance, but he got the right idea that the center of the Milky Way galaxy was out there. Later study found that there was a very, very massive object that did not show any variation in its Doppler shift, but things were orbiting it, indicating a mass of about 300 million solar masses. And scientists said, that bad boy must be the center of the Milky Way galaxy. That can only be a supermassive black hole. And that must be the anchor point for our galaxy. So the globular clusters clustered there as well as out in the halo. Then we have the open clusters. We find a lot of those in the disk. And the associations in the disk as well. The diameter, the size, you see that the size of the globular clusters is much bigger than the size of the open clusters. And the associations I thought were similar size to open clusters, I'm clearly wrong. The mass of the globular cluster, much more mass because you have much more stars. The colors of the brightest are red for globular clusters. What does red tell you about a star? Cool. So if your brightest stars are cool stars, there's only one way for a cool star to be bright. It's got to be not massive, because massive has to do with how much matter is present, but enormous. Right? I mean, we often say massive to mean large. So that's why I'm saying we can't use that word here, because it's not high mass, it's high size. So these are going to be red giants, are the brightest stars in globular clusters. In open clusters, we have red and blue. Blue, what does blue indicate? Hot. But hot stars burn out quickly. Right? Hot stars are O's and B's. They have short lifetimes. So that means that the open clusters have a relatively young age just by seeing that there's blue stars in them. And then, of course, the associations, blue, they're the youngest. Luminosities, let's not worry about that. Gone through enough of this. Oh, where's my link to the, maybe it's on the next slide? Better have the link here. I'm going to go to the textbook directly. This here is a picture of an open cluster. The Pleiades, the reason it's on the lab final is because it's an open cluster that you can see with the naked eye. It's large enough to see with the naked eye, has lots of bright blue stars. Here's the link. Okay. So this here, notice I put it in red. Hypothetical. This is a computer simulation. You wonder, how is it that the stars are so nicely clustered? Because it's computer simulation and not reality. So let's look at how this is done. Who wants to bet that? Yeah, okay, it's working. It'll get there. If I've learned anything, this thing responds way too slowly. When I press buttons, I need to just stand back. Okay. Nothing happens. There was no sound to this one as far as I could tell. So this is showing a cluster, and now it's taking the stars and putting them on an HR diagram. So it took all of those stars. Let me actually pause it. Go back. So here we see all of the stars, and what they're going to do is they're going to take them and separate them by color and then by luminosity. And so the other video I was going to show was showing that process much more carefully. But they're taking all of these stars and they're actually showing it in a graphical format because it's kind of cool. Each star is not lost. It's just moved by color and then moved by luminosity. And so this is what it looks like today on an HR diagram. So once again, remember luminosity on the vertical axis, temperature in the horizontal. And this is showing a time sequence of how those stars have moved. Now, what you should note here is that the stars don't move up and down the main sequence. They move across it. Right? So it's not like the top of the main sequence is where a star begins its life and then it moves down, or the bottom is where it begins and it moves up. It starts on the left and moves to the right. And then as it's dying, it moves off of the main sequence. So going back to our presentation, that was hypothetical. Let's look at a real case. So here's a real case. Is that as pretty as the hypothetical one? Afraid not. But it's real, and what you see is, I'm still on yellow. The stars are on the main sequence here, it looks like they're still coming down. They're still forming. They haven't even reached the main sequence down there. And up here at the very highest point, it looks like it's probably in the process of dying already. So you have stars that are the most massive star dying, the youngest star is still forming. Now this is, as you see, NGC, the new Galactic Catalog, I think is what it stands for. 2264, that's how they label it, so anybody can talk about, oh yes, NGC 2264. Otherwise known as, was it the Christmas Nebula or something like that? Anyway, that's how they name it. And so this is a young nebula, and so they look at these and they say, okay, stars that are 1 to 4 million years old, depending on the mass, are going to be where we see here. Now, if you just had this for your data, you probably wouldn't be very confident, right? They study lots of different clusters to get everything. So here is something that's about 100 million years old. Now here you see very clear. This isn't computer simulation, this is real. They're leaving the main sequence there. So that's where the death is. So you can say, okay, 100 million years, stars that are about, let's say, 20 solar masses are dying. And then these are on the main sequence, and what's going on here? Stars below, let's say about 30 solar masses, have not yet made it to the main sequence. And then the other ones are burning across the main sequence. Here is, once again, real data from 47 Tucanae. Tucanae? Tucanae. Notice this is very different for the luminosities. Here is a luminosity of 1. Actually, yeah, that was luminosity, not mass. My mistake there. I said mass instead of luminosity. Luminosities of about 1 solar luminosity. Temperature of about 1 solar temperature. Makes sense. We have those on the main sequence, but the death point is right there. So the 13.1 billion year old star is right at its death if it's the size of our sun. Remember I said 10 billion, here it's 13.1 billion. We don't have enough detail to say where the actual leaving point is, so I can't say 13.1 is the leaving point. The sun could have already left. But still at the bottom, we have down here, it looks like stars are still coming on. So the smallest mass stars still haven't formed, whereas these stars here are all on their death stages. Now this does not represent the motion for one star because each star will have gone on a different path. This is where they are for different masses. And so you have to look at a whole bunch of these and connect the dots, so to speak, to see what the true path is for a single star. Back to computer simulations, that turnoff point is the point when a star is leaving the main sequence. That's how we determine the maximum age based on the mass of a star. What this doesn't show is the turn-on point. The stars are, it pretends that all stars are on the main sequence and just some have left. No, some have still been forming. Now to our official discussion of the helium flash. So I talked about the helium flash. The helium flash occurs because you have a degenerate nucleus. And so the helium flash was up there at the tip of the graph we had before. And there's a core helium flash here. That's when you have helium start fusing in the core of a star that had a degenerate core. And you come down and it shows very little here, but there is a main sequence here, a secondary main sequence. That second main sequence is when you have stable fusion in the core again, but this time it's fusion of helium instead of hydrogen. Now remember, the helium, you only have 1/4 as much helium as the hydrogen you started with because of the reaction. So there's a lot less fuel, and it's at a much higher temperature, so you're going to have to release a lot more energy per second, and so the helium time is very short. And then when you run out of helium, what's going to happen in the core? Well, you've run out of hydrogen already. Now you run out of helium. What's going to happen?
Helium's going to start fusing.
Well, in the core is going to shrink down some more, get hotter. And then the region outside the core, where you still have some helium, is going to, because you still have helium because the hydrogen shell is still burning out, creating helium there. And then you have a shell of helium that starts fusing inside of the shell of hydrogen. So you have a shell of hydrogen burning outward, and then you have chasing it the shell of helium. And you have a second helium flash from the shell beginning if you reach degeneracy there. Now for our sun, that's going to be pretty much the end of it. It will fuse helium, won't go any further. For more massive stars, they'll do more important things. So here is some information about just lifetimes of stars. So we have, yeah, this is all for our sun, not for all stars. I was thinking, wait a minute. So our sun, it says now a lifetime of 11 billion years instead of 10 billion. I'm not going to argue. I know 11 billion, 10 billion, that's a 10% difference. Surface temperature of 6,000 Kelvin, 5,800, whatever. Luminosity 1 solar luminosity, diameter of 1. It's not going to be constant values when it's on the main sequence. It's burning across. So slowly the luminosity is increasing. Slowly the diameter is increasing. Slowly, what's the temperature doing? Decreasing. So we have these changes occurring slowly over time. When the sun gets to the end of its main sequence lifetime, notice 11 billion years on the main sequence. It'll have 1.3 billion years as a red giant. The red giant will be the stage where it is having the hydrogen shell burning outward. Then it will have helium fusion commence, and it's on the helium main sequence for 100 million years. 11 billion years on the hydrogen main sequence, 100 million years in the helium main sequence. You see, that's a much, much shorter time. And so then it will become a giant again when it runs out of helium for just 20 million years. And then the sun's going to be done. Now notice the luminosity. When it's a red giant, it will reach a very big luminosity. Its temperature will drop a lot, but it will be very luminous because it'll be very big. You see this number out here, 165. Then when it reaches stable helium fusion, the surface heats up again, it shrinks, and it'll be 10 times the size. Then when it becomes a giant the second time, about the same temperature, but much more luminous because it's even bigger. So the sun's going to go through some interesting changes. If you have something more massive than the sun, it will do things far more interesting than our sun will do. If it's more massive, and it doesn't have to be a lot more massive, I think it only has to be about 4 times the mass of our sun. Then you will reach a high enough temperature and pressure in the core to fuse carbon. And if you have a high enough temperature and pressure in the core to fuse carbon, it's basically going to go through the entire sequence. So our sun will stop before it fuses carbon. Carbon is the ash that's produced from helium fusion. We haven't talked about the helium fusion process yet. I mentioned the triple alpha, but that's it. I did mention triple alpha at one point, didn't I? It could have been I was just talking to a student or somebody in my office. Anyway, it will then go very, very rapidly through these additional fusion cycles. Right? You saw the big decrease in time from hydrogen cycle to helium cycle. As you go down, each one is very, very, very quick. So like the last one, the silicon fusion, will be less than a day. But it will have shells burning out, hydrogen shell on the outside, and then you go in, you have helium, carbon, magnesium, neon. You see all these different shells, they're all going to be burning out at the same time in a supermassive dying star. And that supermassive dying star becomes a super large star, making your brightest stars out there. And then when all of this is done, what does it have left in the core? Iron. It says ash. I've been talking about helium like helium's ash, iron ash. Why is it called ash? Because in terms of the processes going on, it's useless. Iron is useless for fusion. Why? We talked about this, a month ago. Iron is the most stable nucleus. It has the highest binding energy per nucleon, which means that it cannot give up energy by fusion or fission. It's where it wants to be. So if you force something to fuse with iron, it's going to absorb energy and cool things down. So iron fusion, not going to occur. And so then what happens? You get to an iron core and everything outside burns out. What's going to happen? The whole thing is going to collapse. And we will study next week what happens when the whole thing collapses with its cool outcomes. And here's my last useful slide. It's also the end of the class period anyway. These are pictures of dying stars. And they're really beautiful, aren't they? That bottom right-hand one I had never seen before. You have, let's see, I think this one up here is the hourglass. This one here is, what, cat's eye? I've got microfuchsia, very tiny stuff down here that describes what all it is. But these are stars that are in their death stages. And that's where we're going to be next week. Not our death stages, but exploring the death stages of the stars. Any questions before we head out?
Is there like why are they all shaped differently?
Okay, this one here, we're viewing it at a very different angle. Right, the difference in the top two is largely the angle we're viewing it at. This here is, I think, a bigger supernova and an older supernova. So I think primarily the biggest difference here is that this one's older. These two upper ones are younger. And this one, I just don't know. Like I said, I've never seen that before. I mean, that looks man-made, you know. It's like Aladdin's flying carpet or something. All right. Let's have a good weekend. This is a picture to try to illustrate the difference that you just asked about. If you're viewing it from this angle, you see this. If you're viewing it from this angle, you see that. That's the answer to your question. All right. Have a happy Sabbath.